Well, good afternoon, everybody. Welcome to the second in our series of trench talks. Today, we're going to talk about pump selection. But the purpose of trench talk to me is to convey some detailed nuances of how to improve our skills at designing and installing and servicing geothermal systems. So I appreciate you all taking time out to join us here today. So let's get started. The agenda, what to expect today. One is I want to review basics, simple methods of understanding and arriving at pressure drop calculations. And then the why. Why is it important? And then we're going to spend some time going through some mechanics, actual examples from simple systems to complex systems. And then, of course, a Q&A session at the end. So the first question I want to pose to you all is, are you familiar with the CV and know how to use it? And right now, Charlie's going to start a poll, and I hope you all can answer it. I don't see the poll here myself. Maybe Charlie, you can let me know if it's up and running.
Hey, John, yes, it is working, it looks like.
Very good. Thank you, Jared. So we'll come back to it after you take the poll and give me a little feedback as to if you're familiar with it or not. So what are the basics? And there's two. There's pressure drop and there's understanding pump curves. So we're going to start off talking about pressure drop. What is it? Well, it reflects the energy required to overcome fluid friction. And it's only friction. We don't have to worry about vertical differences in our piping system or elevation changes. In a closed loop system, the water that falls on one side in a downward pipe is offset by the lift in the upward flow. So we're only worried about fluid friction. And fluid friction is a function of temperature, flow rate, and viscosity. So there's a few things that go into it. But the friction all ends up as heat. And it's important to remember that because excessive pumping energy is essentially adding heat to our geothermal fluid. Now, in a cooling dominated application, that not only means you're putting pump energy into the system, that pump energy is raising your fluid temperature to some degree. And the degree is a function of how efficient your system is, the size of the pump and the amount of head that it has to overcome. So not only is the pump adding energy to the system, if our water temperatures are going up, all the air conditioning efficiencies are being impacted as well. Every degree our loop is warmer than what it could have been is another percent loss in efficiency. And I've seen jobs where pumping energy is what's driving loop temperatures out of sight. So a bad selection and poor control can seriously impact the efficiency of the geothermal system. If you have a flow rate and a pressure drop of any element in the system, be it the heat pump, a valve, a section of pipe, if you can identify a flow rate and corresponding pressure drop, from there, you can calculate a pressure drop at any flow rate. I'm going to walk you through how to do that. This simple formula I've probably used a million times in the last 40 years, but it's the ability to take that reference pressure drop at a given reference gallons per minute. Once you know these two items, you can enter a new GPM. If you wanted to have double the flow rate, so you've got this ratio becomes 2, then you square it, it becomes 4, and your new pressure drop is 4 times higher than your reference pressure drop. And that's pretty important because a small increase in flow rate can start to accelerate the pressure drop of your entire system. For example, here is a pressure drop table directly from the GeoStar 5-ton Aston. And the manufacturer gave us 4 flow rates and corresponding pressure drops at different water temperatures. It's also important to keep in mind that this pressure drop is in pounds per square inch. But typically, when we look at calculating pressure drop in a geothermal system, we're going to be interested in that minimum water temperature, which is the higher pressure drop condition. And then we're going to take this table of different flow rates, different pressure drops. We're also going to add one that is, if you have no flow, you will not have any pressure drop. And from this data, you can see the relationship between flow rate and pressure drop. And this indeed is a parabola or a squared function. So if I look at 8 GPM, my pressure drop is just under 2 PSI. If I double my flow rate to 16 GPM, the pressure drop is going to be 4 times higher. Excuse me. So what's the pressure drop at 15 GPM? How do we get there? Well, we can look at the plot and draw a line up from 15 GPM. And yeah, we can say it's probably somewhere between 5 and 6 PSI. But there's a mathematical way to get there. And we're going to start with the highest flow rate and its corresponding pressure drop. And then we're going to use that formula and start dropping in the numbers. 9.7 PSI corresponds to 20 GPM. We take this ratio, we want to calculate it at 15. So that ratio of 0.75 squared becomes 0.5625. And that is what we multiply our reference pressure drop by. So our pressure drop indeed is between 5 and 6 PSI. But to make it useful when looking at pump curves, we're going to have to convert it to feet of head. So you multiply by 2.31, and at 15 GPM, the Aston 5-ton unit will have a pressure drop of 12.6 feet of head. So the CV, and if we can share the results of our poll, hopefully I can see them, but if not, I'm going to call on you, Jared. Maybe you can share those with me.
They should be shared, but I'll just describe it here. We had 14 out of 19 were yes, 3 out of 19 were no, and 2 out of 19 were not sure.
Very good. So we've got a pretty talented audience here that understands CV. And I'll just quickly go through some of the basics. CV, it's the flow rate at which pressure drop equals 1 PSI. Knowing that flow rate and the pressure drop of 1 PSI allows us to calculate a pressure drop at any flow rate using the formula we just showed you. As a general guide, I try to apply valves or devices at a flow rate that's roughly half the CV. And if I can do that, that means the pressure drop of that device is actually 1/4 of a PSI, or well under 1 foot of head. For example, a valve with a CV of 10 should be used where flow is 5 GPM. And you get a little tolerance there, so plus or minus 1, which makes it suitable for a 2-ton heat pump. Because we're going to want to operate a 2-ton at about 5 or 6 gallons per minute. A CV of 30 would be good for 5-ton, because a 5-ton we'd like to be at about 15 gallons per minute, and that's half of the CV. Understanding CV is a vital tool to avoid scar tissue, because you can pick a valve, throw it into a system, and if you didn't account for its pressure drop accurately, you could end up not having sufficient head to overcome its pressure drop. And trust me, I've got plenty of scar tissue. So let's shift gears and talk about pump curves. The Grundfos 2699 has been the backbone of our industry for as long as I can remember. And this pump curve illustrates the 3 speeds of the current 2699, which is predominantly a 3-speed pump. Now, it used to be we had a single-speed pump, and this solid line represents the older 2699. So indeed, when they went to 3 speeds, they lost a little bit of head capacity, even though the pump's on high speed. And then we also show the 26116. It's a considerably stronger pump, but at dramatically more watts. So you've got to be careful when you apply it. You're going to go from roughly 180 watts to more like 340 watts for the pump. And it only gets you another 6 feet of head at 15 gallons a minute. So this curve is the one we're going to be looking at. It is what probably most geothermal 2699s operate at. I know of very few people that actually dial the pump speed down from medium to low speed. And if we look carefully at 15 GPM, we're going to have head capacity just under 20 feet of head. If we put 2 pumps in series, the numbers on the right illustrate the head, and it's doubled. So it's pretty easy when you put 2 pumps in series, they're both going to handle the same flow rate, and they're both going to generate just shy of 20 feet of head. So when you put 2 in series, you're going to be at close to 40. Let's take a look at the up-and-comer Grundfos variable speed UPMXL, or 25-124. It is a variable speed pump. So the pump curve does look different. These are at different RPMs. So, but what is the maximum capacity of this pump? At 15 GPM, it can produce roughly 28 feet of head. Now we look at a little stronger pump, the Velo Stratus Maxo, which is their current generation of Stratus pumps. And it's kind of remarkable because a lot of the control algorithms that we want to use are built right into the pump. This illustrates both what we call a variable delta P curve and a constant delta P curve. So you get these angled lines, they illustrate the control, the operating control set point of a pump. So when you set it up, you pick a head that you want to deliver. And let's just say we want to have 42 feet of head under max flow. And the curve that it's going to follow is 42 feet at max flow, but at zero flow, the other end is half of that. So roughly 21 feet of head. So if we apply this in a system where the flow is constantly varying, the pump will automatically change speed to produce a head pressure that keeps it on this control curve. Now, the other option is a constant delta P. So it will maintain the same head regardless of flow rate. So this is a little different pump curve. And to me, it's ideal for geothermal applications. And if we look at its maximum head capacity at 15 gallons per minute, this 1.25-inch pump can produce just shy of 50 feet of head. So it's much stronger than a 2699, roughly 2.5 times stronger. The why. Why are we so concerned about pumping and pumping energy and pumping selection? Efficiency is sacrificed when we aren't diligent about sizing a pump and reducing the head requirement in our system design. As I pointed out earlier, pumping energy turns into heat, which raises loop temperatures, which causes the air conditioning efficiency to further be compromised. So it's a double whammy whenever we use excessive pump energy. And a lot of mechanical designers and engineering firms, they've been taught to size pipes based on a phrase, 4 feet per 100, which means the pressure drop per 100 feet of pipe. If it's 4 feet of head, then we've got the right size pipe. But in our industry, that is no longer acceptable. We can't be, if you're just designing piping systems within a building, that might be fine, and the runs are not that long. But we're dealing with hundreds of feet of pipe. So if I'm dealing with a 500-foot loop in the ground, and that's 1,000 feet of pipe, if I use this philosophy, that's 40 feet ahead just in the loop. The supply and return piping, we could run hundreds of feet to get out to a distribution manifold. So this methodology is simply no longer acceptable. And I'll share with you a little story. Back nearly 25 years ago, I did an energy audit of a geothermal system in Pennsylvania. And it was as bad as you can imagine. The circulating pump used more energy than all the heat pumps combined. And it's because the engineer who designed it did not want to use two-way valves at every heat pump. And the pump was set up to run at full speed, 24 hours a day, 7 days a week, 365 days a year. And it was outrageous. And they wondered why their operating costs were so high. So we recommended to go to variable speed, put two-way valves in, and we dropped the energy consumption by about 90%. So to summarize, if we try to save a nickel or two by pipe sizing and making it a little smaller, we're sacrificing the investment that's been made into a geothermal system. Tens of thousands, hundreds of thousands, $1-million loop fields are being compromised by how we go about sizing pipe in a system. And we need to focus on keeping pressure drop low and not penalizing the system for the life of the system. want to walk you through a quick example. 5-ton Aston, the table you were exposed to earlier and are familiar with. But when you apply it in a design of a system, you have lots of choices. So let's go with flow rate. The manufacturer gave us quite a range of flow rates. They go as high as 4 GPM per ton. In a closed loop system, I don't like going below 2.25 GPM per ton. But for the sake of our demonstration here, let's start at 20 gallons a minute, because more is better, right? Antifreeze. I could spend a lot of time talking about antifreeze, pros and cons, but that's for another trench talk. But let's simply stipulate that we're going to use 23% propylene glycol. Loop field configuration, and this is the meat of where you need to be diligent in sizing, piping, not only from a thermal performance standpoint, but from a pressure drop standpoint. So you've got lots of choices, horizontal or vertical, number of circuits, loop pipe size, both length and diameter. So for today's exercise, we're simply going to start with 4 3/4 inch by 800 foot horizontal circuits with a buried manifold roughly 100 feet from the house. Supply and return pipe. How do we get out to that manifold? We've got some choices: 1.25 inches, 1.5 inches, or even 2 inch. Let's start with 1.25 inches for the 100 feet run. Now, this is a little calculator I put together many years ago. It's definitely out of date because it's still got my old fax number there. But we've got 20 gallons a minute. We're looking at 2699s. And this simple schematic sort of illustrates the flow path and the corresponding sections. So the first section from the flow center to the heat pump, 35 feet long, 1.25 inches, 6 elbows, polyethylene. It's calculating a pressure drop of 3 feet of head at 20 gallons a minute. The heat pump, our 5-ton Aston, is 22.4 feet ahead at 20 GPM. And since we're operating at 20, its pressure drop is 22.4. We got to get 100 feet out to the loop manifold, 1.25 inches. The earth loops, we got 4 circuits at 800 feet. And coming back from the manifold, we got another 100 feet of pipe. It says this system at 20 GPM has 100 feet of head pressure drop. My software only went to 4 pumps. However, when you look at this curve, this is 1 pump, 2 pumps, 3 pumps, and our 20 GPM is literally off the chart. So could have been, here's 4 pumps, here's 5 pumps. We might need 6 pumps to make this system work, which obviously is not acceptable. So what can we do? 1, let's change the flow rate down to 2.5 GPM per ton. All the pressure drops get recalculated. Our heat pump drops from 22.4 down to 8.8. Our earth loops drop from 58 feet down to 26 feet. At 12.5 GPM, this system will present 43.6 feet of head total pressure drop. But obviously, a Reynolds number of less than 2,500 is undesirable. Hard to truly keep it at 2,500, but let's do one thing. Let's change the antifreeze. We're going from propylene glycol to methanol. And bingo, our Reynolds number now becomes acceptable. And pressure drops drop slightly. We're down to 38.3 feet. And on our graph, we're showing where that point is on our system pressure drop curve. We could stop now and go with 2 pumps, and we'd probably have a flow rate of about 14 gallons a minute. Perfectly fine. But let's see what else we can do. Let's increase the number of circuits from 4 to 5 and decrease the length of pipe from 800 to 600. Dramatic reduction in the loop pressure drop. Our Reynolds number is still acceptable. And now our system pressure drop is 27.5, 2 pumps. But boy, we're real close to letting 1 pump do the trick. So let's do one more thing. We're going to change our 100 feet out and back from 1.25 inches to 2 inch. And now we've got 22 feet of head, a single pump. Now, I will admit this pump curve is the old single speed 2699. The 3-speed is going to be close, but it may not quite make it. So trying to get away with 1 pump on a 5-ton system is very difficult. And there may be times you can do it, but by and large, we're going with 2 pumps on a 5-ton system. So the moral to that story, every detail of the system design can and does influence pump selection. You've got to do your homework and look at every element. To own your design, you need to understand these dynamics. And I've dealt with a lot of contractors over the years, and many of them do not. Design tools to quickly evaluate your choices will help avoid scar tissue. Now, I'm sure I'm going to get a question in the chat box about, are our design tools available to you? And unfortunately, no, they are not. I do not want to be in the business of supporting software. I'd much rather support you in helping you learn the fundamentals and encourage you to make your own design tools, because that way you know what's behind them. Multiple heat pump systems. This is a much trickier calculation. Each heat pump circuit must be evaluated, but the same basic principles still apply. So here's another calculator we use to evaluate multiple heat pump systems. The first section, we try to capture some system details, like how many ton, what kind of antifreeze, how many heat pumps, how many distribution manifolds. We can accommodate up to 5. We have different pumping arrangements. We can have a basic, which is a single pump. A dual is 2 pumps in parallel. Stacked is 2 pumps in series. We can do primary, secondary with 1 pump going to the loop field and 1 pump going to the heat pumps. We could also do dual primary, secondary, which in essence is 4 pumps, 2 on the primary side, 2 on the secondary side. We pick a pipe material for the interior piping. We definitely going to use polyethylene outdoors, but picking a different pipe for indoors can affect your calculations. In this section, we try to capture the loop field characteristics. How many groups? We've got 2 groups of 5 for a total of 10 loops. We've got 600 feet of pipe in the borehole, so the borehole is 300 feet deep. We're going to use 1.25 loop. We're going to use TR11. What kind of manifold do we have? Is it reverse return or is it a short manifold? The manifold length, is it, I put in 4 feet with 1 foot spacing. It's a short manifold. It won't affect pressure drop to a great extent. How long is it to get out to that buried manifold? Again, we're going to use 100 feet. We're going to specify a size and a DR. And then there's some common pipe. Once all the flow comes back together and it has to handle 100% of the system flow, we can specify how long that pipe is and what size pipe we're going to use, as well as the DR. When we look at the heat pumps, we specify each of the heat pumps. In this case, we've got two 5-ton heat pumps, a 4-ton, a couple of 2-ton heat pumps, and a 3-ton. We have a reference flow rate and pressure drop. We're going to specify a pipe size feeding each one, the length of that pipe. What is the two-way valve CV rating? And on the bigger ones, we typically use a CV of 30. And on the 2-tons, we're going to use a CV of 10. A balance valve, and I'll come back to this shortly. Which manifold is it? Well, they're all on the same distribution manifold inside. Here we can adjust the flow rates of each heat pump. And over on the right, we sort of calibrate, say, where are we in terms of GPM per ton? And frankly, if you're above 2.5, even as low as 2.25, it's very acceptable. But I'd like to stay up from a design standpoint, 2.75 to 3 GPM per ton. It does all the calculations after we dial in a different flow rate. We get a pressure drop of the piping, the two-way valve, the heat pump pressure drop at the lower flow rates, the manifold, our distribution manifold is calculated. The balance valve, if we need one. Now, what I try to do is I dial in different flow rates is make the total pressure drop on every heat pump almost equal to each other. You dial it in. And on the 2-tons, I couldn't dial it in close enough. So I had to put more resistance to flow in that circuit. So I've put a balance valve and I can dial in the exact CV I'd like for that balance valve. And that allowed me to bring the total pressure drop in line with all the other heat pumps. So now this system is balanced. The next thing we look at is pumps. We have all the different Maxos and even some Grundfos Magna 3s to choose from. And we've adopted the 1.5" by 3-52 pump. And these pump curves, this is the variable delta P pump curve. And the two plots shown here is the green line is the pressure drop of the loop field. The red line is the total system pressure drop, because we always want to maintain a certain pressure drop, roughly 18, 19 feet across the heat pumps, but we have antifreeze. So it's really 25.4 feet of head across the heat pumps. So that's got to remain constant at any flow rate, whereas the loop field, its pressure drop is going to 0. So these variable delta P control curves are almost perfect for geothermal systems where the loop field pressure drop and the heat pump pressure drop are pretty close to each other. In this case, our loop field pressure drop is 19.9 feet. Our heat pump pressure drop is 25.4. If they were radically different, we may have to go to a constant delta P curve, because this red curve may come out of the envelope up in this area. So something to keep in mind in doing calculations as well. But let's take a look at the 1.25" pump. Maybe I can save some money. So we're going to change it to the 1.25", and suddenly we're outside the operating envelope of the 1.25" pump. So that gives us the ability to quickly look at different pumps to meet the need. And this is the summary table. It gives us the antifreeze correction factor, pressure drops, The total system pressure drop of 45.2 gives us a rough volume calculation, how much antifreeze we need. And if we want 100% redundancy, that is an option we can plan for. But otherwise, if we have a dual pump, we're planning on needing both pumps to accommodate full flow. But each pump by itself can handle about 2/3 of the requirements. So you've got some redundancy if one pump were to fail, but you've managed to get by with a smaller pump by letting them share the duty for max load. And this would be our recommendation for a flow center. It's got 2 Velo pumps in parallel. They combine back together again to feed the heat pumps, come back from the heat pumps, go out to the loop field, and come into the flow center here. Another output of our software is to itemize each of the heat pumps and their performance based on AHRI ground loop rating. It also selects a two-way valve as well as balance valves. So we can identify a good balance valve for only those heat pumps that need it. And we also give you a pressure drop across that balance valve in inches of water column. So if you're out there balancing, you can just take a reading across this valve and dial your flow rate into 6 gallons per minute. And then we could talk briefly about really big jobs. And I won't spend long on this because it just takes all the same basic calculations that we just walked through, but it applies it to every pipe in the system. And I'll give credit to Jared Fortna. This is a job at Skidmore College that he went through and analyzed some 300 different sections of piping. He could flip a switch up here with a pull down menu to look at different piping materials. And as a result of this type of analysis, we were able to show that we could get away without using steel pipe, go to PPRCT, and actually improve the cost effectiveness of the job. The contractor priced it out, and he came back with a lower price to go with PPRCT. And a lot of that was based on this type of analysis. So with that, I want to thank those who contributed data and information to this presentation. And I think it's time to open it up to questions and answers. Hopefully we got answers. So Jared, I'll be looking to you to guide us through that.
Well, at the moment, we only have 2 questions. One was, will you be sending us a copy of Excel, which you already addressed. And then the other one was on the GV calc. Chris asked, ZV, CV, is that the motorized valve at the heat pump?
Yes, ZV for zone valve or two-way valve. Yes, it's the CV rating of that valve. So you can also raise your hand, and maybe Charlie can help manage and unmute you if you want to ask any other questions. I'd also encourage you, Charlie, I has activated our evaluation poll, and I'd appreciate your feedback. Certainly helps us gear future trench talks. And you can certainly go to our website and submit topics that you'd like us to cover. So don't be bashful. You can submit anything. We're not even capturing your email. You just fill out a simple form and submit topics. And we will factor that into our future planning.
John, I assume these are going to be available on YouTube at some point.
Yes, we will put them on YouTube. We will also put them on our website. Maybe I can show that. Do you see my website here, Jared?
No, only the Q&A.
Ah, interesting. That's what Zoom doesn't do. It doesn't shift to the screen. Go to, there's that website. Share. How about now?
Yes.
Okay, this is our website. And if you go to the mechanical room and Trench Talk Library, we're going to keep posting our recordings here. Here was the first Trench Talk, and you could actually download the slides if you want them. But we're simply going to be adding Trench Talks to this library. And here's where you can submit your suggestions for future Trench Talks. So just throw some ideas in there and hit the submit button and we'll get it.
A couple of questions here, John. Joe Canoza is asking, he says, I assume you would help to do piping layout on larger projects if we obviously use GeoStar and your pumps.
Yes, indeed. We're in this to make a profit. We'd be glad to help out any customer in designing projects, and hopefully we can provide at least the flow center and hopefully the heat pumps. We do have an extensive library of all the different heat pumps out there. So if you're working on a job that even specifies something other than we sell, we'll work with you, but we would hope to get the flow center part of the project.
Okay, another question here. Rob asked that the Velo variable speed pumps with adjustable head pressure are expensive. Can you validate the monetary savings in using these pumps versus a constant speed pump?
Yeah, certainly we've analyzed pump operating cost under a lot of different scenarios. And almost routinely, we come up with energy savings in the 80 to 90% range when using these types of pumps. ECM variable speed pumps have incredible turn down. And certainly many years ago, we used variable frequency drives on end suction pumps, and that's still a common practice. But when you look at the turn down capability, it's just not there. And in these systems, we want to see turn down to about 10% from peak load. And typically we don't see that with VFDs. But if you're just going to throw a fixed speed pump in and let it run and ride the pump curve, yeah, you're looking at 85 to 90% energy savings. So on a particular job where you're looking at the cost of electricity and the cost of the pumps, the incremental cost of the pumps, I'll leave that up to you to do the math. But every time we've looked at it, these ECM pumps are ideal for geothermal applications. And they're ultimately cost effective because somebody's investing literally hundreds of thousands of dollars to have geothermal. And if we saved $2,000 on a pump or pump station, are we really doing the customer justice after spending so much to get geothermal?
Okay, just as a kind of a side question, when do you think it makes sense to use variable speed? In other words, does it make sense to have a variable speed pump on a single heat pump or 10 heat pumps?
That's a good question, Jared, because you and I have debated that many times. And certainly the incremental cost on a single heat pump application, if the heat pump is variable speed, then yes, I want to use a variable speed pump. But if it's a dual capacity heat pump, single application where you could put a simple 2699 or two of them in, that's probably your most cost effective for a single heat pump application. And even going to two heat pumps, you really don't have enough diversity to justify variable speed. But certainly going to 3 or 4 or 5 heat pumps, without a doubt, a single variable speed heat pump or circulating system can be justified.
And then Rob also asked, can you comment on the relative life expectancy of variable speed pumps versus constant speed pumps?
Unfortunately, I really can't. I think we've been using Velo pumps now for probably at least 10 years. Generally very good reliability. And we've had the little circulators 2699, so some of them fail prematurely. So I feel comfortable saying that the reliability of both pump types is relatively good. It's not as good as we'd like to see it because we do occasionally get failures, but it's a pretty robust pump.
Okay. And then Chris asked, he just checked the CV rating of a 1-inch TACO zone century valve, and it states a CV of 8.9. And so he's asking, is it only good for 4.3 GPM?
Well, it's interesting because if you look at the 3/4 inch TACO century valve, it has a CV of 10. Now, it's identical valve, but with a transition reducing fitting to allow you to connect a 1-inch pipe to it, but that sudden drop in diameter needs to be factored into the pressure drop of the valve. But I would say the 3/4 or the 1-inch are both perfectly fine on a 2-ton system. But it's kind of interesting to note that the 3/4 inch has better flow characteristics than the 1-inch. But I think it's strictly because of the sudden reduction in diameter at the entry and the exit of the valve has an impact. But going, it's a guideline to look at half the CV as an application point. The difference between a 1/4 PSI or a 1/3 of a PSI pressure drop is trivial. So I wouldn't hesitate to put an 8.9 CV on a 6 GPM application. Yeah, the pressure drops can be slightly higher, but not enough to worry about.
And the pressure drop of your heat pump is relatively low, then that added pressure drop, that doesn't have any impact on the overall system.
Right. Certainly, if you're forced to put a balance valve on any particular circuit, then using a two-way valve with a lower CV may be appropriate in that you're creating the extra resistance with that two-way valve, and maybe you can avoid the need for the balance valve. So those are the details that you want to look at.
So that's the end of our questions.
Okay, I want to let you guys go home early. I think we're approaching Miller time. So thank you very much for joining us, and hopefully we'll see you next month. So take care.